Okay, welcome. A fine Tuesday afternoon, and it's going to be very hot today, apparently, here in San Marcos, so that'll be fun. Okay, so I'm going to go over Chapter 5 goals 1, 2, and 3, and then I might actually get to Chapter 7 goal 1, and the primary reason I want to do that is I want to have time for our exercise on Thursday. Our exercise on Thursday is actually going to be assigning R and S's to everything, because I think that is one of those skills that you really need to have to be able to answer those questions correctly. And it takes a little time to actually do it. I have my method where I use my hand, and you'll see that in the video, but I have two other methods that I want to record a separate video on. And when you look at that, it's if the hand thing is not working for you, look at the other two methods, find one method and only use that, okay? So don't try to mix the different methods together, just use one method and then just figure out which one works for your way of visualizing things, and then that should get it really solidified in your mind. Once you get it, the idea of, getting the priorities, arranged in your head correctly so you can assign clockwise or counterclockwise, that's the hard part. It's, clockwise and counterclockwise are pretty easy to remember, etc. So, okay, the chat room is open. So if you have any questions, go ahead and ping me. I have started recording this time. Thank you for reminding me from last time. And it looks like we have 18 of us already, so that's good. We have about 23 total, counting me in the class. So, all right, I am going to start sharing my screen, and let's see if my iPad will cooperate today. Yes, there we are. All right, so we're going to do Chapter 6, chirality, and the major goals here are: number one, how to do our 3D drawing. How to take a stick drawing and turn it into something 3D that we can play with in our heads. The different isomers possible associated with that, because we have, stereoisomers, and then we have R and S, but then we also have diastereomers and enantiomers to assign as well. And so getting those kind of together in a, putting the faces screen over here so I can still look at you if you want me to. And then the last thing is the element of finding symmetry and mirrors. Okay, finding the symmetry and mirrors is something you just gotta try a few times, and then you start seeing it again and again. But that's why I wanted to bring it out as a special goal. Note, I don't have R and S assignment in the goals, because that's gonna be part of our work in class group activity on Thursday, and a separate video that I'm going to show you 3 different methods. So, but if we can do the 3D drawing part correctly, that means that it should help us in the assignment of R and S. Okay. So the key thing we need to first think about is that, number one, even if we draw it flat on a page, all of the structures have a 3-dimensional element. Remember, we're looking at sp3 hybridized carbons, which means that they're at a tetrahedral shape. And so they're going to be nice, 3 things are going to sit on the table and 1 thing's going to stick up. And so we have to keep that in mind when we are doing these structures. Excuse me. So if we look at just this structure here, notice all 4 of these look a little bit different to us. However, they all represent the exact same compound. Okay, so the fact that they all represent the exact same compound means we have to figure out how to translate what we see into that 3-dimensional shape, or understand what the different segments of each shape means. So obviously, the first thing we need to start with is assignments. And so in general, when you have just straight lines in between atoms, or just straight lines in the zigzag form, we tend to call those are in the plane of the paper or the object that they're written on. So in this case here, all of these carbons for that zigzag pattern here, actually, let me switch to a color. All of these zigzaggy lines are in the same plane. And so that means that the outward facing, the solid wedge is coming out at us, and the dashed wedge goes behind the page. So in number 3 here, I think it's easy to see that if those carbons are all in the plane, that OH is sticking out at us and that hydrogen is sticking back, okay? Now, because a lot of the times we do not draw the hydrogens, representation 4 is exactly that same representation, but we need to remember that if it's not specifically assigned, the other thing is hydrogen. And we also have to remember that each and every one of these carbon with 4 bonds around it is a tetrahedral structure. And so they all have will have 3 bonds in the plane and then 2 things out of the plane. So there's 3 atoms in the plane and then 2 out of the plane. So let's think about just that concept real quick here. We have in structure number 1, this carbon, and this O, this oxygen are all in the plane of the paper, okay? So as long as we can clearly identify that in our heads as those being in the paper, then what that gives us is the idea that now our hydrogen is behind the plane of the paper and this ethyl group is in front of the plane of the paper, okay? Now, what's really going to help us with this is also being able to then take this kind of tetrahedral structure. I like to have it drawn such that it's sitting like it's on a tabletop, because then when we do that, we can take the top atom and do rotations around it. So we can rotate it 60 or 180 degrees around to help us identify, oh, are they mirror images? Are they enantiomers? Do they overlap? And so I really like representation number 1 for what we do, because that way you can just take it and pick it up and turn it 180 degrees and say, does it match or does it not match? And so that's really important. Okay, so, so that being said, let's go ahead and practice a couple things where we're going to take representation number 1, we're going to do 2 things to it. We're going to, not only are we going to redraw it in our own hand drawing, but we're going to then draw its mirror image, and then we're going to take that mirror image and rotate it 180 degrees, okay? And so I want to show you some functions that we can work with it to make it such that it's how I do it, and I think if you use these steps, you'll be able to see how we can verify that the molecules are the same molecule or different molecules. Okay, so the first thing I want to do is I'm going to redraw that in a stick form representation such that I can draw a mirror image next to it. So in a stick form here, we're going to do our OH up here. I'm going to leave the CH3 here as just this stick right here. This CH2CH3 is going to be that. And I'm actually going to draw the hydrogen here. The reason I want to draw the hydrogen here is because we do have to assign its priority when we look at RNS. So I'm going to keep it there to show us where it is. Okay, and so we have this filled wedge coming out at us. So this is the CH2, this is the CH3 at the end here. Okay, so all I've done is redrawn that exact same thing, but only using assigned atoms. And all the sticks and bonds are the hydrogens and carbons that we have, and only the OH has to be identified. So when we do that, we want to think about, can we draw its enantiomer? And when we try to draw its enantiomer, we want to have a mirror outside of the atom, and we want to draw the mirror image of it. And so when I draw the mirror image of these things, what I like to do is I like to start from the thing closest to the mirror and draw outward from it such that it looks like a mirror image. So I'm going to start with this methyl group at the end of this chain, and then I'm going to draw that filled wedge in here, and then the OH on the top here, the stick going back, and then the hydrogen going here. Okay, so because I started at the mirror and moved outwards, keeping all the connections and basically the same kind of wedges, it's just going in the opposite direction, I believe I've created a true mirror image of our first compound here. So this is our first isomer, and then this is our second isomer here. Okay. So, but remember, in our definition of chirality, it has to be a mirror image that is non-superimposable. Right now, our ethyl group is pointing toward it and our methyl group is pointing in a different direction. So one of the ways we try to look for this is we take one of the structures, and in this case, we're going to take the one we just made the mirror image of, and we're going to rotate it 180 degrees, okay, around a single axis. So that's why I like having it on the tabletop there, because then you just take it, imagine all three of those atoms on the bottom here stay touching the table, and all we're going to do is rotate around the axis that is sticking up. Now that axis happens to be that carbon-oxygen bond, and so all I'm going to do is rotate each atom slowly, one at a time in our minds and on paper, to show you where it would end up by doing that rotation. So we're going to rotate around this bond here, and so we're going to start with having our OH and our bond to our central carbon here, because that's not going to move, right? That's the axis we're rotating around, so we're not going to move that. So the first thing we want to do is we want to take the thing in front of us, and this is our nice, solid wedge. So if that solid wedge were to go and be rotated 180 degrees, that would end up putting it somewhere back here. So, because that's 180 degrees away, and the solid wedge would turn into a dashed wedge. So that's the first thing we're going to do, is we're going to take this atom and move it to the back as a dashed wedge. And as we rotate it around, that means that little stick continues out over here. Okay, so we've moved one of those bonds 180 degrees. Okay, now let's go ahead and move the next bond over 180 degrees. Now, the next one we want to do is we want to do this one, and it's in the plane, right? So if we rotate it around 180 degrees, it's still going to be in the plane, but it's going to be on this side of the axis now. So we're going to draw that one now too, okay? So we have two of our bonds have rotated 180 degrees, and we're left with our last one, okay? So our last one here, this hydrogen was sticking back, so that means it's going to be sticking out toward us when we rotate it 180 degrees, and it'll be 180 degrees from what it was, so it's going to be on this side of the axis. So we're going to redraw that one now, and because it's coming out at us, we're going to draw it as that dark wedge, and then we're going to assign it as a hydrogen here. Okay, I'm going to redraw that with black because that's what our thing is here. So by moving each atom one at a time, we are less likely to put it in the wrong place. And if you look at the end here, we have a methyl group, then a hydrogen, then, if we go clockwise around, we had a hydrogen, a methyl group, an ethyl group. Clockwise, we have a hydrogen, a methyl group, an ethyl group. So they're in the same order if we go around clockwise. So the atoms at the bottom are all in the same order. They have changed position by 180 degrees. Now we think we have a good representation of the material. And now notice, let's compare the one here on the right with the one here on the left here. Now we have three of the atoms are in the exact same position, right? These right here are in the exact same position in both molecules, which means then we can now directly compare just the remaining two atoms to see if they coincide or not. And if we start doing that, we see that there is an ethyl group on our original number 1 compound, but there is a hydrogen in that position in our number 2 compound. Therefore, the hydrogen and the ethyl are not equivalent, therefore they are not superimposable, okay? We know that this is the mirror image because we drew it, we did the rotation so we could see if the other groups aligned, and they don't. So we know we have a non-superimposable mirror image, so we have the pair of enantiomers that we needed to assign R and S. Okay, questions on that?
Yes, quick question. So this hydrogen on the last drawing, the blue hydrogen,
Yes.
it's not superimposable because that hydrogen is not matching up with the methyl group over on isomer number 1 down here. Correct?
So yeah, let me, so this hydrogen right here, that hydrogen is on a solid wedge, so it's sticking out at us. If we look over here, this has a CH2, CH3 group, or an ethyl group sticking out at us. So therefore, we're comparing that CH2, CH3 to a hydrogen. They are not the same, and therefore that is not superimposable. Okay.
Gotcha.
So yes.
Thank you.
Okay. So once you do this a few times, you'll see that, you know, you'll get these little functions of rotation and mirrors. It just takes some, you know, practice, you know, a few times. There's a couple good examples in the book, and if you run through the book and do that plus the homework, I think you'll start seeing all these different mirror planes, etc. Okay. Okay, so let's continue on. And so I've actually done what I was going to do there. Let's take this compound here and redraw it in that tetrahedral structure. All I'm going to do is just redraw it to show us how we're going to translate it. Okay, so because it's drawn this way, we know that we have, you know, these 3 carbons are all in the same plane. So if we keep those 3 carbons all in the same plane, but we know that we have to have that last remaining atom, which is that hydrogen in the back here. When we convert to a tetrahedral structure, we want 3 atoms sitting on the table. So we have a couple things we can do. We can say, oh, let's just keep the 3 carbons in the same plane. Let's put the 3 big atoms in the same plane. What I like to do is take the highest priority thing and put it on that z-axis, okay? Now the reason is because we're gonna have to start with that highest priority as number 1 anyway. So the idea is, how can we get it so our highest priority atom or connection is up in that z-axis sticking off the table? And in this case, the oxygen would be our highest priority atom because we follow the same priority rules we had for E and Z. And we'll notice that, so the only thing we need to do to get this structure to sit down on a table is to make sure that, let me do it in red here, that this atom, and this hydrogen are the ones touching the table, because that means the oxygen, our highest priority, is going to be sticking up. So when we draw that, we start with the highest priority as a straight line, because that's our z-axis. And we'll take one of the materials that was already in the plane and keep it in the plane. And in this case, we're going to keep this methyl group in the plane. If we set this hydrogen down onto the plane, it's still going to be behind here, but it's going to be just rotated down slightly. Now, what does that do to this atom and this thing that it's attached to it? Okay, it can't stay in the flat plane anymore because we've rotated it, right? So what happens if we take that flat plane and we rotate it down here is that part is now kicked out toward us. So that's where we put our solid wedge here with our ethyl group. And that's the translation of that flat drawing to that tetrahedral drawing that lets us do that rotation we have. The other thing we can see here is that if you have 2 straight lines and a dashed line, that means that the last thing you have is a solid wedge, okay? So, or if you have 2 straight lines and a solid wedge, that means the last remaining thing has to be a dashed line. So as long as you have each of those elements in your structure, you should be translating it correctly, okay? Questions on that? Okay, so let's do another conversion of the mirror image, taking one enantiomer and creating the other enantiomer with that mirror image. Again, it doesn't matter how complex the molecule is, you know, this is, you know, something I use, you know, frequently because I'm old, but but it doesn't matter how complex it is. If we follow the same procedure every time, we will get the correct answer every time. So again, we start with our plane out here on the side. I like to start on the side that's closest to our chiral center, just because you know, that way you can pay close attention to what's happening. Okay, so again, we start where the first atom is the first atom we draw, then the next atom, and the next atom, and the next atom. And that was a solid line, so we're going to draw a solid line. Okay, now the next thing we have is a big wedge right here, and that wedge has a CH3 on it. I even drew the H as the mirror image, just because I think that might be interesting. So now the hydrogen is going back with a dashed line. So we're going to go the hydrogen back with a dashed line. And then we have a nice solid line going to this structure that we'll later learn as a benzene ring. And then we'll just draw the rest of it down here. Okay. So even though it's a complex molecule with 15 or so atoms in it, by starting at the inside and working your way out and keeping everything in the same orientation, you have a high probability of drawing the correct enantiomer. Okay. Now that that's there, let's assign R and S real quick. Okay. So again, I like to use my hand as the system. And if we look at the structure here on the left, the blue structure right here, I like to have my hydrogen as my hand. I like to draw that hydrogen back so it's easier to do. So when I do that, I see this is my methyl group here. I see this is my benzene right here, and I see this is my COOH. Okay, that's going to be our carboxylic acid eventually when we learn those. But so that being said, this COOH has the highest priority because it has heavier atoms than carbon. So this is going to be 1. Okay, this benzene ring where my thumb is going to be 2 because it's got double bonds in it, or multiple carbon bonds. And then this H is going to be 3, and the methyl group is going to be 3, and of course the H is going to be my wrist. So if I'm looking at this, if I turn it around, we have 1, 2, 3, 1, 2, 3, and that's counterclockwise. And so the isomer on the left here is our R because it's counterclockwise. Now, go ahead and do that same thing with the one on the other side, okay? And again, you can use your left hand if you want. It doesn't matter which hand you do it.
I'm sorry to interrupt. Are you showing us your hands?
Yes.
I don't see that.
Do you see? Oh, you don't have, my video has me actually showing my hands. Okay.
Yeah, sorry.
All right, so write the structure down.
Okay.
And let me actually stop sharing, and I'm going to show you my hands. Okay.
Gotcha. Thank you.
Stop sharing, and I'm going to put you in speaker view. Okay. So can we see my hands now? Okay. I am sorry. On my videos, it actually has my image as well as what I'm showing. So I looked at that. So on our image that we had right there, I like to have my wrist back here as H. And then I just start assigning everything based on the orientation of how it's drawn. So on our image there, the methyl group looks like it's pointing up the most. So this is where my hydrogen, my methyl group is. That COOH is to the left of it. So that's on here. And then that that benzene ring, which has carbon-carbon bonds, is going to be here, okay? Because this is facing up, kind of poking toward us. The hydrogen's poking back, and the COOH is on the left side, and the benzene ring is on that right side. Okay, so our priority is the COOH is highest priority, followed by the C carbon-carbon, followed by the CH3, and then the hydrogen's back here. So that means 1, 2, 3, 1, 2, 3. That's counterclockwise. Assigning 1, 2, 3. And so that should give us the R isomer, okay? Now, when you look at the other isomer, it's actually pointed the other way, so it might actually be easier for you to use your left hand. And it doesn't matter as long as the wrist here is your lowest priority, it doesn't matter which hand you use. So in that case, we have, again, our hydrogen, our CH3 is still at the top because it's pointing up. Our COOH is toward the middle of this plane. It is on the mirror side here. And our C double bond our C double bond C bond is over here. So we have, this is still, COOH is still our priority 1. The C the carbon-carbon-carbon bonds are number 2, and that carbon-hydrogen-hydrogen bond is number 3. So we have 1, 2, 3, 1, 2, 3. And if we turn it around, this is going clockwise. So that clockwise is going to be R. And I said that wrong. This is counterclockwise. This is S, and this is R. Okay, sorry. Counterclockwise is S, and clockwise is R. Okay, now I'm going to share my screen again and talk you through that one more time. Again, looking at your hand, if you have, I'm going to switch over to red ink here. So on this side over here, if you looked at your hand, this methyl group here would be the index finger. This group right here, the COOH would be the middle finger, and this bond here would be your thumb. And so that'd be 1, 2, 3, and that should be clockwise, which should give us the R configuration. Okay, does everybody see that? If not, don't worry, I have another video where we're going to go through all that again, but to meet some of our other goals, I'd like to continue on. Again, just getting that in your head, practice that a few times, and we have our exercise on Thursday. Okay, so practice it a few times today and tomorrow, and if you still don't get it by Thursday, let's go ahead and do a Zoom meeting so we can all get it together. Okay.
So on Thursday, we're going to be doing examples like these with the groups?
Yes,
Okay.
after the noon, after the 1 to 1:40 group session is going to be assigning R and S as groups.
Okay, cool. Cool, thank you.
All right, so let's show another way of assigning R and S here. So in this case, right here, in these structures, we have some different structural elements here, and we've already assigned them for a priority. Chlorine is number 1 because of, its high Z number. The one assigned number 2 has a carbon and a carbon bond. Number 3 is just a CH3, and of course H is last. And so if you look at that and you use that hand structure again, where hydrogen is where your wrist is, the chlorine is going to be your index finger. The the CH2CH3 should be your middle finger, and then the 3 should be your thumb. And so when you do that, you should get a counterclockwise rotation, which means it should be S. Okay? And so try the last one again, the last one here at the bottom, right here. Notice there's a ring there, okay? All that ring does is tell you that, number 1, you have 2 different groups on there, because the 3 carbon there, the one that's assigned 3, has a CH2 on it. The one that's assigned 2 has 2 carbons bonded to that carbon, so that's like a carbon-carbon-carbon. So that's assigning it as 2. The oxygen is assigning 1 because it's the higher Z number, it's the higher atomic number. And so if you assign, again, your hand with the OH as your thumb, your middle finger as the carbon-carbon double bond, and your index finger as the carbon-hydrogen-hydrogen bond, or that CH2, you should get that going in a counterclockwise, that's a clockwise, sorry, a clockwise rotation, which should be assigned as R. Okay, so that's how I do it. And again, if this is not working for you, I'll have 2 other methods on my next video. Okay, so now to complicate things, when you have more than one stereocenter, you have to keep track of both of them. And so when we go to our diastereomer pairs, remember that our diastereomers are anytime you have more than one chiral center, you only have enantiomers for that pair that is mirror image and non-superimposable. But notice between the top one and the bottom one here, okay, the OHs are on the same side on this side, and they're on opposite sides of this one, okay? That means that they can't be mirror images of each other, okay? So that these two are not a pair of enantiomers. However, they could be each a component in a pair of enantiomers, okay? That being said, let's use another way of drawing our mirror images again by doing that same process, but now we have two chiral centers to play with, okay? So what I'm gonna do is I'm gonna draw the mirror here, and again, I'm gonna put it right here, and we start from the inside and move out, so that would be an HO, HO, and a solid wedge, and a solid wedge right here. The next thing that we have is that center line of carbon-carbon and the CHO up here, and we're going to keep that dashed wedge, and we're going to keep this dashed wedge as CH2OH, and then we have a solid wedge with a hydrogen and a solid wedge with the hydrogen, okay? So again, that's how we draw that mirror image of it. We just start from the inside and work our way out, keeping all of the wedges the way they were. All we're doing is working from our inside out to draw to that correct mirror image, okay? Now in this case, because this group is different than this group, we do not have a mirror plane. We don't have to worry about finding a meso compound. And so because these are mirror images of it and they have different groups on the top and bottom, they cannot be superimposable. So we know we've drawn it correctly. Okay, now for this last one, we're going to do the exact same thing on the bottom one, and it'll do, let's see, HO solid wedge, H solid wedge, C, CHO, CH2OH, and then a solid wedge with an OH over here, because we have to match this side, and a solid wedge with an H over here, okay? So again, using that mirror plane conversion, starting from the inside out, we will typically get to those correctly. And again, because these are mirror images, this set here is a pair of enantiomers. Because these are a mirror image of each other and non-superimposable, these are a pair of enantiomers. Because we have two chiral centers, and other than the connection of basically this atom here on both of these, they are identically chemically except for where that group is in space. That means these four compounds are diastereomers, okay? So we're able to convert from 2D drawings to a spatially resolved 3D drawing and then make our mirror images and rotations. Those are the three most important things we wanted to play with today on these, this structure here. Okay, we can do the exact same thing on cyclic compounds because we do all the same processes. We just start with our mirror plane again, and then HO solid wedge, line solid wedge, CH3, and then we just draw all the other connections here, okay? So you can also do that on the other one. It doesn't matter if the functional groups are facing away from the mirror or toward the mirror. As long as you follow that process, you will always get the correct drawing of the enantiomer. Okay, so on after we're done here, you can try drawing that last one as well. Okay, so let's look at this one right here, and we want to look specifically at looking at possible symmetry elements in them, okay? So when we draw this as our mirror image, right here, we will just start with our material here, 5-membered ring, OH is a dashed one and a solid one here, OH, okay? Now, we need to see if these are the same compound. So the first thing we need to do is think, okay, can we rotate the compound? Or is there a plane of symmetry within the compound? So this is where it starts to get a little complicated. We have to start thinking of things in a couple different ways. Okay, so when we think about a plane of symmetry right here, the first thing we think about is, okay, we have an OH on this side and an OH on this side. So can we place a plane of symmetry somewhere in between those two different groups, those two OH groups, such that they would be like a mirror image on a pond, okay? So let's imagine putting a plane of symmetry here, cutting through this atom and cutting through this bond right here. If we did this, this OH is sticking out, and therefore its mirror image would be sticking out. And if we had, so that means that this atom alone, all by itself, cannot be in a symmetrical, is not symmetrical, because that atom would be, the OH up here is actually back, but the mirror image through this plane would be forward. It would have that solid wedge still, okay? So in this example, we do not have a plane of symmetry. And if we do not have that plane of symmetry in our compounds with two or more double bonds, that means they are not meso, okay? That definition of meso is if we can find somewhere in there where if we cut the molecule in half, it's exactly like the top and bottom, or the left and right are exactly the same, that means that that is that plane of symmetry, and that takes away the chirality, okay? So in the cyclic structures, it happens more often, and it also happens, you can cut through the middle of a bond or through an atom itself. It doesn't matter. So that's one of those tricky things about finding that plane of symmetry, is being able to think you can cut through atoms, you can cut through bonds. Okay. And then on this one right here, the last thing about doing these chiral things that I really think that a lot of people kind of gloss over is the fact that, okay, we only have to pay attention to a compound if it's chiral if it has 4 different groups, okay? A lot of times I will see lots of people try desperately for an hour to assign the chirality of this compound right here, and they get R half the time and S half the time, and they're really, really confused about how it happens. Okay, how many different groups do we have on that central carbon right now? Okay, we have the OH, we have the dashed hydrogen, okay, those are different. We have the wedged CH3, and we have the straight line CH3, okay? Now, those CH3s are equivalent. Therefore, this is not a chiral compound, okay? It only has 3 different groups attached to that center carbon, okay? So, first thing you do is count to make sure all the different groups are different. Now that they are all different, assign priority. Once you've assigned priority, you then figure out whether it's clockwise or counterclockwise, okay? So I can't stress that enough. Double check to make sure that your chiral center is chiral. Now, looking at this compound here, let's double check that all 3 of those stars have 4 different things bonded to them, okay? So if we pull this up here and look at this, okay, this one, we say it's a chiral carbon. Let's double check. So we have a CH2, a CH, and then a CH2 and a CH3. Oh, but let's not forget, we have a hydrogen back here too. Okay, so that CH3 is at least 1 different group. That hydrogen's another different group, but we have 2 CH2s. Okay, when we can't tell in priority, we have to go to the next atom over, right? So we have a CH2 and we have a C with an OH. So that means we, number one, have two different CH2 groups there. And this one is the higher priority than this one right here. So now let's reassign the correct priority in the blue ink here. We have a CH2C. So that's a higher priority than the CH3 here. So this is a higher priority than that. But we have the CH2CO. So this is a higher priority than this one. So that's going to say in blue color here, this group is our number one priority because it's proximity to the OH. This group is our number two priority because of the carbon-carbon bond. This is our number three priority because it's the CH3, and that leaves our hydrogen as priority number four. So we, number one, found four different groups on there, and we assigned our priority correctly. All right, and we're going to do this a little bit quicker for the last two, just so because we want to make sure we get it, but not beat it too hard to death. So obviously the OH is one. We have a carbon bonded to two other carbons, a carbon bonded to one other carbon, and don't forget the hydrogen as our fourth group. So that truly is a chiral center. Okay. And this one right here, it only has a methyl group and a methyl group and a hydrogen in this carbon. So that means it's not chiral. So we don't have to worry about that one. And of course, our last one here, because the oxygen is bonded to the CH2, and this is a CH2, and this has a carbon with two other carbons hooked to it, that, and of course, don't forget our hydrogen, that gives us our four different groups. So we can assign a chiral molecule or a chiral center to that atom. Okay. Okay, so now notice in this slide here, the last thing I want to look at is you can draw that mirror plane anywhere you want. All you have to do is follow the rules. And so what I'm going to show you is I'm going to draw the mirror plane here instead. That's not where I drew it last time. That's not where I drew it any of the other times, but it will work. Dash, 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 CH3, solid wedge. Oops, going the wrong way. And then a straight line to a COOH. And then a straight line to a benzene ring with a benzene ring. And then this has to go up here, CH3, because this one is far away from here, so it has to go up here. So you can draw that plane anywhere you want. And as long as you start from the mirror out, you will get the correct enantiomer. Okay, so this is my 3D drawing goal for chapter 6. Any questions on this real quick? Okay, while you're typing in your stuff into the group chat or chiming in, I'm going to go ahead and switch over to our next goal. Which is isomers. Okay, so I used those words when in our last one, but now I want to really get to, you know, kind of the definitions and how to recognize things. And so that's where we're going to go here with isomers. Okay. Actually, it is 12:45. So why don't we go ahead and take a break right now? Come back at 12:55, and we will start on our second unit here. Okay, so come back at 12:55. I'm going to stop recording.